Hi guys, welcome to this video on basically the introduction to a branch of calculus we call integration. And we're going to start off by looking at the area under a curve, which is all about what is part of what integration is all about. So to start off with, we're going to take it right back to the basics of it. We're going to look at rectangles underneath a curve and see if we can't work out what the area is. So I've got this curve here, y equals 1 plus x squared. And what I want to know is what is the area underneath the curve between 1 and 4. So what we're going to do, we're going to do it two ways. We're going to look at it in two ways and then compare the answers and then see what we can do with those numbers. We've got here lower rectangles and upper rectangles, and I've drawn them in here already, so it saves a bit of time. So lower and upper. The difference is the height is equal to the minimum value of the curve. So in this case, when x is equal to 1, we're going to work out what this here is. So from when x is equal to 1, the area of that rectangle, I'm going to add to it the area of this rectangle here and the area of this rectangle here. So we're using the values when x is equal to 1, which will give us the height. So if we plug in the value here, it'll give us the height. Again, when x is equal to 2, x is equal to 3. So let's do that one to start with. So I'm going to call this A with a sub L to indicate it's the lower one. Now I've got these as 1 unit each, and I'll show you that a bit later that it will change depending on what we've got here. So I'm going to have 1 times f of 1 plus 1 times f of 2 plus 1 times f of 3. So f of 1, if we just plug that in there, is going to be, we could actually take 1 times out of all of this and make it a little bit, factorize it. If x is equal to 1, when we've got 1 squared, which is 1, plus 1, which is 2, plus when x is equal to 2, well, 2 squared is 4, plus 1 makes 5, and then is 10 for the last one. So all of this will add together to be 17 units squared. What about the upper one here? I'm going to use a AU for it. 1 times, I'm just going to put everything, because we're still using 1 as our interval width, I'm going to just take 1 times out to start with. So in the first one here, we've got the height of it is when x is equal to 2. So it's going to be f of 2 plus f of 3 plus f of 4. So see here, x is equal to 2, x is equal to 3, x is equal to 4. If we go through and work this out, well, we know the first two are going to be 5 and 10. Plus 4 squared is 16, plus 1 makes it 17. All of this will then equal 32 units squared. So the area under this curve lies somewhere between 17 and 32 units. So we could say that the lower boundary we could write it like this. So the area is somewhere between 17 and 32. It's not very accurate at the moment, considering that 17 units squared, if you almost double it, you get 32. Well, if you double it, you get 34, so it's only 2 squared units off. So how do we make this more and more accurate? Well, what we do is we make these rectangles smaller and smaller and smaller, the width of them. So if we want to make these rectangles, instead of them being 1 unit wide, we want to make them half a unit wide, what we'll have, and it's a slight change to the formula, but we'll have, instead of it being 1 times the whole way through, it'll be half times, because the half here and the 1 here represent the width of the rectangle in how many units in terms of x. So what we'd have is, we'll start off at f of 1, but the next one, instead of being f of 2, we're going to add half onto that, so it'll be f of 1.5. And this is going to keep going on and on and on until we get up to, would be 3.5 for this side. Over here would go from 1.5, because that'll be the upper one, up to 4. And you can see that this is just going to get longer and longer and longer, and to do these calculations by hand is going to get more and more tedious, especially when we divide it up. Instead of it being, in this case, we've got 3 sub-intervals. When we've got half, we've got 6 in total. As it keeps getting, as those sub-intervals keep increasing, the width of the rectangles is going to decrease, and it's going to, the equation is going to get longer and longer and longer and longer. And this is when we need to use our calculators to work out, to get them to crunch the numbers for us, because that's what they're good at. I'm not sure what it is for a Casio, but on a Texas Instruments TI-84, you've got this app called Area Approx. If you search for that in TI-84, you'll come up with this, download it, put it on your calculator, or alternatively come and see me and I can transfer it across, and this will calculate it for you, and I'll show you guys how to do that in class. What you'll notice, as we increase the number of sub-intervals, the width of the triangle will width of the rectangle, will get smaller and smaller and smaller. What's going to happen with these two numbers is they're going to start to converge. The areas, the total areas, will start to get closer and closer and closer together. Eventually, if we make the number of sub-intervals large enough, then the numbers are going to be the same. But to do it to calculate those by hand, it will take forever. So this is the start of integration, and we'll talk about how we can actually do the integration side of it to get the answer to this in a very short amount of time with minimal calculations. But it's good to see where this has come from, because this is how it all started. It all started with looking at rectangles under curves. There's also another method with trapeziums under curves, which we won't go through that for the moment. That we might have a look at a bit later on. Hopefully it's made a bit of sense, this video. If you've got any questions, just ask and go through them. Thank you for watching, and we'll see you in class, and we'll go through this in a little bit more detail and get you guys to do some examples with it. As always, thank you for watching, and we'll see you next time.